Welcome back to our lecture series in engineering mechanics. And as I promised to you in our last lecture, we will now expand our knowledge to look at the equilibrium of particles in a 3D coordinate system so that we can actually analyze systems as they exist in the real world. For some reason, students sometimes initially are a little bit afraid about 3D systems, especially when it comes to calculations in 3D. But my goal today, of course, is to show you that all we have to do is expand our already existing knowledge from the 2D world so that we can move into the 3D world. And the reason we are doing that is so that we can calculate the forces in 3D cable structures. That is our first step into 3D systems, so that we can talk about that on a general level. And to ease us into the topic, I also want to use this as a chance to talk about symmetry or structures with symmetry, to show you that there are some conditions that you can take advantage of when you solve these problems. And ultimately, of course, our absolute goal in this lecture is to really calculate randomly oriented cables in 3D structures so that we can be prepared and solve any scenario that will be thrown at us. So without any further ado, let's get started and talk about the equilibrium conditions in 3D. And the best place to start, as I mentioned before, is by where we left off. So let's go ahead and start with a two-dimensional coordinate system. And usually we have a two-dimensional coordinate system which looks like this, x and y. And what we've learned so far is that all we have to do is say that we have the sum of the forces in x being equal to 0. And then we start our actual equation. And we also state that x is positive to the right. And we did the same for the y-axis. So the sum of the forces in y is equal to 0. And we defined that as upwards positive. And now I'm going to draw a coordinate system that I usually don't draw in this class, with the z-axis coming out of the plane. You see that in other classes. In this class we usually don't do that, but my goal is to expand our knowledge. So I'm going to make this the z-axis, the positive z-axis. And so what that means for my equilibrium condition is that now I add another equilibrium condition, which of course reads the sum of the forces in the z direction being equal to 0. And I have to state that it's positive in the diagonal outside of the plane in this case. And what that means now is that we are ending up with one more condition. So we had these two conditions before. We now have a third condition. And I want you to think about this for a second, what that really means. And let me take you back to the 2D condition. What we did when we had 2D systems was we always solved for two equations with two unknowns because we had these two conditions. So this allowed us to solve for two unknowns. And the reason for that is because we had two conditions. But now we are actually adding a third condition. So now we added a third condition. And therefore we can now solve for three unknowns at a time. So solve for three unknowns at a time. And that, of course, is very important to understand. So let's highlight this, that you can solve for three unknowns because you have three conditions now. Now, what that means is that our math becomes a little bit more complicated because, of course, we're having three equations now and we need to solve three equations with three unknowns at a time. But what I will show you initially is that often you can take advantage of some aspects of the structure to reduce it to one unknown or two unknowns. Of course, at the end of this lecture, we will be ready to solve all three equations with three unknowns at a time. But again, my goal here is to show you that 3D equilibrium problems are not as scary as you might think they are. So let's move on and let's go to the equilibrium equations in 3D. And to do that, I'm now going to draw the correct coordinate system that I usually use in this class. And that means that I usually have the x-axis coming out of the board and the z-axis is going upwards. So remember our right-hand coordinate rule. So let's say here I have x, and here I have y, and then here I have z. And probably to better orient ourselves in the coordinate system, it's better to also add the negative direction. And then I'm going to place, let's say, two forces in here. Let's use a blue force that goes somewhere into the third octant. Let's say that goes here. And it goes all the way into this direction. And then I also want to add a second force. Let's make that purple. That actually comes out of the board in this case. And so I'm going to make that look like this. I have to parallel move my axes. So that I, of course, have all three components. And let's call this F1, and the other one I'm going to call F2. And you may already notice that this system could never be in equilibrium, so I'm going to add a third force to it, because right now everything is just pulling up. Right? Let's take a look. This is going in the positive z direction, this is going in the positive z direction. So this system could never be in equilibrium. In fact, this should from now on make you clinch. You should say, why is there nothing to balance these two upwards forces? So I'm going to add a downward force right at the center. This could be like, for example, our traffic light that's hanging there. So I'll add a force right here at the coordinate origin. And there's the point that connects them. And let's call that F3, which only has a z component. So now I can go ahead and actually develop my equilibrium conditions and equations. And of course, my conditions for pictures like this, I can always blindly write down as first the sum of the forces in x is equal to 0. And the sum of the forces in y is equal to 0. I can do that without even thinking about it. And the sum of the forces in the z direction is equal to 0, because that has always to be true. Now I need to take a look at the diagram and see in which direction those forces are acting. So x is moving in that direction, Fy is going to the right, and Fz is going up. So now let's develop our equations. So I can say that 0 is equal to, let's start with our F1, which is going in the positive x direction, so plus F1x, and F2 is actually going in the negative direction, so minus F2x, and then there's no F3 acting in that direction because F3 is just in the negative z direction. For the y direction, I have to start with my F1 as well, which again is positive, so plus F1y minus F2y, and no F3 component. But in my last equation that looks different, so now I have to state that we're looking at positive F1z and positive F2z, but minus F3. And that is literally everything you have to do, because now you have established proper equations with three unknowns effectively. Well, Actually, sorry, that's not really true. Right now we have up to 9 unknowns here, but you already know the trick that we have to do next. So right now we have f1x, f1y, and f1z, and those are 3. And then we have f2x, f2y, and f2z, and those are another 3. And then you could have the same thing for the third direction, which here we don't do to get the problem across. But you know the trick that we have to do to turn these equations into 3 equations with 3 unknowns. We would have to express these forces now, or these force components, in terms of their parent force, if you want to call it that way. So, for example, you somehow can turn F1 into F1x, right? So I can use this force and project it onto the x direction, for example. And that, of course, is best shown in an example, but please understand that you can express this, this, and this in terms of F1. In fact, let's, for that force, write down that here we have F1x, and here we have F1z, and here we have F1y. And of course, I know that they point in these directions. Otherwise, they could not move from this point to this point. And I say that again so that you develop a good 3D understanding of these problems. So to move from this point to the end of F1, you can either go along F1, or you can, for example, go to the right first, then out of the plane, and then upwards. And that's how you assign the proper directions here. And that is important so that you understand where the plus and the minus is coming from. Of course, I did this without these arrowheads here already, but this will clarify this a little bit more for you. So that means that we can use these equations and conditions in 3D as well. And just for our general understanding, because it's so much fun, this is the 3D equilibrium condition. And then what we see here is the 3D equilibrium equation. And that will always work. Again, of course, you have to express them in terms of 3 unknowns. So that will be our next step. So let's go ahead and write that down. So ultimately express these functions in terms of 3 unknowns. So that means in this case f1x, f1y, and f1z all are expressed through f1. Likewise, f2x, f2y, and f2z are expressed through f2. So these are the important ones. Let's highlight them. So this is what you really have to plug into your equation ultimately. But again, that is best shown in an example. Just for clarification, this down here is the free body diagram in 3D, and I encourage you to always use this to express your equations. And my experience in the classroom is that sometimes students don't want to draw, or sometimes students think that drawing is a waste of time. I would beg to differ a lot on that. The more you draw, the better understanding you develop of the 3D problem, and the more likely or the less likely you are to make a mistake here in your equation. So I always encourage students to draw the free body diagram no matter what, if it's requested or not. But that concludes the introduction to the equilibrium in 3D. And now, believe it or not, we are already ready to move on and solve our first problems. Let's go ahead. So here we can see our first 3D problem, the 3D cable structure. with a spring included. The spring actually goes from node A to node B. And our problem here states that we are supposed to determine the stretch in spring AB. And you already remember from the previous class that we worry about this at the very end. So first we have to find all the forces in the cables. And let's look at this cable structure here. So first of all, we have 90 pounds acting downwards. That's the weight, the traffic light or whatever you want to put there. Then we have a cable that goes upwards. And now take a look at this 3, 4, 5 triangle. It states clearly that the 3 is parallel to the Z direction and the 4 is parallel to the X direction. So therefore this hook here actually resides within the XZ plane and it has 0 Y component. So this cable has no Y component. Similarly, this cable here, it can be a little bit deceiving, but notice that there's only the 30 degree given here. So that means that D actually resides within the X negative Y plane with a 30 degree separation from the negative Y axis. And then clearly, I think, is stated that AB is along the Y axis. So now we can solve this. And maybe the first thing I'm going to do is actually superimpose a little free body diagram. And since I can zoom in here and make sure that we understand that it's really acting at this node, I'm going to draw the free body diagram for node A here. And what I will find is that I have forces in all 3 directions, but differently distributed over the cables. So for example, I have a force that is acting in this direction, and that here would be, let me zoom out, that would be AC, right? So ACX in this case. I also have a force that's going upwards, and that is ACZ in that case. And as I mentioned before, that cable has no Y direction, so I'm already done with that one. Let's move on to the next cable. Let's say we're going to do AD next. So AD has no Z component, but it definitely has a Y component that goes in this direction. So I'm going to call this ADY, which is acting in the negative direction. And I have also a X direction force. So let's draw that one. Let's say that's acting right here. Of course, in reality, that's right at the node, but it shows it better at this location. So ADX. However, in reality, it's actually acting right here, right? So this is another representation of ADX. And last but not least, I have the force in the spring. And that force is acting in this direction, and I call that AB. And that is technically ABY. So it's equal to AB in this case. And for completeness reasons, I probably should also add the forces, the entire forces, the summation of them. So let me add the blue one first. So I have a force here, which that is pulling in this direction. Call that AD. And then I have AC along this line here. So I'll call this here AC. Before I move on, let me just clarify that we effectively superimposed the free body diagram on the sketch, which is not the right way to do it, but just to get the point better across here, since we're not in the classroom together. Let me just explain one last time my cut philosophy here. So I cut the system, let's say here, maybe here, maybe here, maybe here, and it doesn't really matter how large it is, because so I have this entire cut system here. And I could, of course, also cut, let's say here or here or here, but I want to make sure that we all understand that we're pulling on this node here at the origin of the coordinate system. So this is actually a coordinate system for an introductory problem, so that the coordinate system coincides with that free body diagram, if you will. This may be different on later problems, but I hope you understand that we're just looking at that one node. And that is one reason why, for example, we can ignore the spring, for example, right now, and we can move our way through the problem now. So let's go ahead and do something that we would never do in practical applications, but from an educational standpoint, it's the right thing to do. And that is writing down blindly the equations and, of course, before we do that, the conditions. So this is something I would do on an exam if I wasn't properly prepared. I would just blindly state that the sum of the forces in the x direction is equal to 0, and the sum of the forces in the y direction is equal to 0, and the sum of the forces in the z direction is equal to 0. And of course, I need to state my directions. X is going in this direction, y is going in that direction, z is going in that direction. And now I can just write down my equations. Of course, all of them start with 0 is equal to something. So let's do that. And then I want to start with my smallest one, which is AB. So in the x direction, there's nothing in the AB direction. In fact, AB only has a y component. And then next is AC. And AC happens to be in the negative direction, so minus ACX. And then last but not least, ADX. And that is positive, right? So plus ADX. And of course, there's nothing actually in the negative direction. So I don't have to worry about that. This next row is the y direction. So here we have plus ABY, so plus ABY. And then we have nothing in the x direction, but we have a negative ADY, so minus ADY, and nothing in the z direction. Maybe we'll show this here. Last but not least, I have the z direction where AB has no z component. You start to see why this is our first introductory problem, right? Because it's becoming very simple now. In the AC cable, of course, I do have a z component. So this is plus ACZ, and then the next cable has no component, so I cross that out. But I have minus 90 pounds here. So that now is my equation. And once again, if you are experienced and prepared, you probably would have not needed to write this down. I will show this to you in a second. But for your educational experience, I will now show you how to convert these equations with these many unknowns, 1, 2, 3, 4, 5 unknowns, to 3 equations with 3 unknowns. So for example, I can express ACX in terms of AC. And how do I do that? Let's get started. So AC is really nothing, ACX is nothing else than AC divided by 5. And in the x direction, I have a 4, so times 4. Now, for my AD, which is my blue color, I have ADX, and that is the sine direction of 30, if I'm not mistaken. So plus AD sine 30. And I'm done with that row. Now, for my next row, for the y direction, y is just equal to AB. I don't need to worry about this. I don't need to worry about the red component, but the blue component minus AD, which now is the cosine of 30. And then last but not least, I have the z direction, which only needs to convert ACZ, which is 3/5. And then minus 90. So let's be clear and just highlight what I really would solve for here. So let me pull out my ruler and my highlighter and state that this is the equation that we would solve. This is the equation that we would solve. And this is the equation that we would solve. And to do that 100% correct, I probably should state to you that we have a 0 here at the beginning. So 0 is equal to, 0 is equal to, and 0 is equal to. And what you see now is that you have three equations with three unknowns, right? So we have AB, AC, and AD. And so I can solve this system of equations now. But now it's definitely not my goal to show you how to solve three equations with three unknowns. You have the tools to do that already if you reach this class. The point here is to teach you mechanics. So let's actually go through the problem like I would probably go through it in the real world. And so for that, I'm going to use my logic now. And you will see that by doing that, I can just solve it. So what is my logic? If I look at this system here, there's 90 pounds pulling down. That means that I have to pull 90 pounds up. And the only cable in the system that can actually pull up the 90 pounds is definitely not AB and is not AD because they have no vertical components. So I immediately know that this component must be 90. So let's actually do this even with writing down real numbers here. Let's just say that ACZ is 90. So I know that that is 90. Now I can calculate my other components. I can say that ACX is 90 divided by 3, which is 30, multiplied by 4, which is 120. And so now I know all components in AC. Of course, I could also calculate the magnitude, which would be 90 divided by 3 multiplied by 5, which then becomes 150, but we don't even worry about this, but just for completeness reasons. What I'm really worried about, or what I really want to continue with, is the 120. Because the 120 is pulling in the negative x direction now. And the only thing that can balance that is definitely not AB, right? Because AB only has y components and we're looking for x components. This has no x component, this has no x component. So the only thing left is AD. So I have to pull out of the plane because this is pulling into the plane. So I already know that this component ADX is equal to 120 pounds. And now you see where I'm going, right? Because now I can just take the 120 and turn it into AD. So for example, AD here, right? This force AD times the sine of 30 gives me 120. So let me write that down. Just so AD times sine 30 would be equal to 120. And so therefore I know that AD is equal to 120 divided by sine 30. And that comes out to be 240 pounds. Maybe I should add that here, pounds. And now, of course, I can calculate ADY to be 240 multiplied by cosine of 30. And if I run the numbers for that, I find that that is 207.8. 207.8 pounds. And now I can continue with my logic, right? I know that this node here is pulled to the left with 207, and the only thing that can pull it to the right is actually the spring. And so I know that the spring now has to carry also 207.8 pounds. And now I'm almost done. Don't get me wrong. We still have to calculate the stretch in the spring. That was the actual calculation. But what I just showed you in physical terms, or like working my way through it, because it's such a nice, easy problem that only has like one vertical and then two horizontal and two in the y direction horizontal forces, that I actually don't even needed this. So this is a very favorite example of mine to get this point across, because every mathematician can solve this, but what engineers need to be able to do is this. And so I hope you get that point, and I hope you understand this. Of course, later on you will not get away with working your way through this, because problems are not always that simple, but in the beginning, this is the way to learn this kind of stuff. And I encourage you to really think about that and understand this. And also maybe validate it, like run the 3 equations with 3 unknowns here and find hopefully the same answers that I just did. But now to calculate the stretch in the spring, let's do that. So the stretch in the spring, so stretch AB is equal to, I always remember my formula that the force in the spring is equal to K times S. And so S is F over K, right? So what is the force that is acting in that spring? It is 207.8 pounds divided by 500 pounds per foot. And so our answer to that is 0.4157 or 0.416 feet. And that is the result, so we double underline it. Be careful, sometimes these problems ask you to find the stretch in terms of inch, and then of course you have to do one more conversion step here, and you have to master the imperial system and multiply this number by 12 to end up with inch. But this concludes this problem now. We solved it, and I believe the engineering approach in this case was much easier and faster than the equilibrium approach or the setting up the 3 equation with 3 unknowns. So now we're ready for more complicated problems, so let's move on. So now our problems can become a little bit more interesting, like this cable structure here, a true 3D cable structure that appears complicated on the first glance, but we will see a few things that can help us in a second. Let's first look at the problem description. So there's a box that has a volume of 3.5 cubic yard and is completely filled with water. Based on that assumption, calculate all the cable forces. And then later on, there's a bonus point for assuming that the box is filled with concrete. We'll talk about that at the very end, instead of water, of course. So let's only focus on the actual initial problem. So we have this box here, which is suspended on a cable that is completely vertical and only directed along the z-axis. But we also have cable AC, AB, and AD. And let's talk about AD first, because that is probably the simplest one, because it has only a force in the x direction. So that one does not contribute in the uplift of the box. But AB and AC do, and that seemingly makes it complicated, but I want you to understand the symmetry of the system. So take a look at these dashed lines here. So for example, node C is actually 8 feet in the negative x direction, 4 feet in the positive y direction, and 6 feet in the z direction. So that is pulling, if you will, towards us. And away from us with very similar components is AB. And what that means is that the system has symmetry about this dashed line, if you will, or I should say about the x-axis. So let's write that down actually, because it is important. So symmetry about the x-axis. And that means that I have half of the weight on the one side of the x-axis and the other half of the weight on the other side. So I can actually simplify my work. So I can actually think of it as half a system. And let me draw that into this here. So let me pretend that I have a force in this direction, in this direction, and in this direction. And my arrows heads go in this direction. So let's call this here, for example, ACX, ACZ, and ACY. And of course, I can do that for the other cable as well. Let's do that just for visualization purposes. So I have this component, this component. And the last component, which my ruler does not play along, but it's going in this direction, and this direction. So I can call this ABX, ABZ, and ABY. And you can already tell from this picture now that these two forces together, ACX and ABX, have to be balanced by AD. ACZ plus ABZ have to balance the actual weight. And then ACY balances ABY. So that's how you generate the balance here. And that's why you can actually state now that due to symmetry, AB is equal to AC. And you can also say, for example, ABX is equal to ACX, or ABY is equal to ACY, and so on. Actually, let's complete it because it's so simple to write it down. ACZ. So now I can say that 1/2 of this weight has to be balanced by one of the forces, right? So let's say ACZ has to hold this. So I already know that whatever the weight is of this box, I have the weight in the uplift here. So the first thing, of course, to do then is calculate how much force we have due to this completely filled box with water. So let's analyze that first. So weight of box with 3.5 cubic yard of water. And the first thing we need to know, and of course you know this already, you looked this up a long time ago, is that water in the imperial system has a weight of 62.4 pounds per cubic foot. And that is usually the unit that engineers use in practical life, pound per cubic foot, and not per cubic yard, because we can use this to convert to cubic yard. But be careful, students often fall into the dimension trap. Then they understand that 1 cubic yard, or sorry, I should say 1 yard is actually equal to 3 foot, right? That's the linear dimension. So 1 yard is equal to 3 foot. And then sometimes they think, okay, I'm not going to fall into that trap, so I have to obviously multiply that by 3 for whatever reason I don't understand, because they understand that we're not dealing with linear dimensions here, but we're also not dealing with square dimension with an area. We're dealing with a volume. So in reality, 1 cubic yard is actually equal to 3 foot times 3 foot times 3 foot. And so the answer is not 9 cubic foot, which is an answer I often get in the classroom. It is actually 27 foot cubed. And now you can use that 27 foot to calculate how heavy this box is, right? Because now your box is 62.4 pounds per cubic foot multiplied by 27 cubic foot per cubic yard is the way to write this. And then, of course, we have to multiply it by 3.5 because that's the multiplier of the box. And what you will find is that your box actually now has a weight of 5,900 pounds, or roughly 5,900 pounds. And that I can now continue to use to find my forces. Let's go back to our picture here, and maybe I even add this here, 5,900 pounds. And I'll say it again, this 5,900 pounds is supported by ACZ and ABZ together. So each one of them has to carry half of that, right? So I can already state that up here. I can already state that this is equal to 1/2 5,900 pounds. Now, because I have one component of the triangle given, and we already learned in so many previous classes how to convert one component into all the other components if we have the geometric arrangement given, and we definitely have the geometric arrangement given here, I can calculate all other forces. So I know again 8, 6, and 4, and I can now use that to calculate the rest. So for example, the length of the cable, right, that comes to no surprise. I can calculate the length of the cable by saying that, let's use red here, so LAB is equal to, of course, AC as well, but it's equal to 6 squared plus 4 squared plus 8 squared, and then square rooted the whole thing. So that is the square root of 98, if I'm not mistaken. So I can use that now to calculate all my components. For example, if I want to calculate the force AB, let's do that up here because it's more visual. So the force in FAB, so, or maybe I should use AC actually in this case. So let's say FAC is equal to 1/2 5,900 pounds. That is the component in this vertical force. So I'm going to divide that by 6 feet. So I divide it by 6. And now I want to find the force along this cable, which of course has a length of square root of 98. So now I multiply that by the square root of 98. And what I will find is that FAC is actually equal to 3,478. 3,478 pounds. And once again, I did that through the geometric arrangement. So I used Pythagorean in 3D up here, and then I used the components. So I used the ACZ component, divided that by its geometric description, 6, and multiplied it by the geometric description of the one that I wanted to know. So in this case, I wanted to know AC, and so it was this description right here, which was 98. All right, but what I'm interested in next is the force in this cable here, AD, and so I need to find ACX for that, right? So I need to find ACX and actually multiply that by 2 because ABX and ACX, they together pull on this cable. So let's look into that. And for example, I can calculate this one here as 1/2 5,900 divided by, and now I need to be careful again, I need to double check myself, divided by 6 multiplied by 8, because that's the direction I want to find. So multiplied by 8 divided by 6. That is the component that I need. And so now all I have to do when I want to find the answer to my AD, let me visualize that as well. So I'm going to find AD now. So this is AD, and AD is nothing else than 2 times 1/2, and I can cross that already out, 5,900 divided by 6 multiplied by 8. And if you calculate that out, you will find that we're looking at 2,213 pounds. 2,213 pounds. And that actually solves the problem, right? Because I also already know that my FAC is equal to FAB, and therefore I have proper results here. I have the result up here, and I have the result down here. And of course, in an exam, I would write that much more neatly at the bottom of the page, but I need to keep the bottom of the page to now use the equilibrium approach, the equation approach, to write these equations down so that you can actually validate your understanding of that. But this would technically be an engineering solution to the problem. We solved all the cable forces based on the fact that we have this box filled with water. Now, like I mentioned, let's complete this from an equilibrium standpoint. So if I don't know what to do on my exam, for example, the best thing to do is to blindly write out these equations. So the sum of the forces in the x direction is equal to 0, sum of the forces in the y direction is equal to 0, and the sum of the forces in the z direction is equal to 0. And of course, proper definition of the directions. And in this case, it's a little bit different than we've seen. So my y direction is actually going in this direction. My x direction is almost horizontal. And my z direction is going up. All right, now what do I have? 0 is equal to the x direction first. So plus AD, I'm going to put that at the end actually. So I'm going to start with AB, so minus ABX minus ACX and plus AD, right? Plus AD. For the y direction, I have minus ABX, sorry, ABY, plus ACY, and nothing in the AD component. But for the z direction, I have plus ABZ plus ACZ, nothing in the d direction, but I have minus 5,900 pounds, right? And again, what I now have to do to solve these equations here, notice that we have 1, 2, 3, 4, 5, 6, 7 unknowns. And obviously I cannot do that, so I have to use the geometric description to express, for example, ABX in terms of AB and ACX in terms of AC. So let's do that for one equation, and then I think we're done with this problem. So let's say that AB, of course negative, is, and be careful now, AB is this one here, which has a length of, let me get you that information on the screen. So that has a length of square root of 98. So I divide it by square root of 98, and I'm looking for the x direction, which is 8. So that means I have to multiply it by 8 and divide it by the square root of 98, right? And the same is true actually for AC. So minus AC square root of 98 multiplied by 8 plus AD. For the y direction, it would be almost the same thing, except AB divided by square root of 98. And now in the y direction, it is multiplied by 4, right? So multiplied by 4 plus AC for square root of 98. And last but not least, the AZ direction is also divided by 98, but multiplied by 6. And plus AC 698. All right, but we don't need to solve this now because we would just find the same answers as this. This, however, here gives you a chance to really solve these equations if you don't see the engineering or how the forces go through the system. So, and there's nothing wrong with not seeing that initially. You can definitely work your way through every problem by using this. And just to be clear here, let me add the lines through that so that I drew them too close to each other. I apologize for that. But now you have these equation sets that help you to solve this. In every case, this will always work, right? No matter what, this will always work. Whereas for the approach up here, you probably need a little bit more experience. So as a beginner, you probably use this, but try to see what I showed you here. Nevertheless, this completes our second problem of 3D particle equilibrium, and I hope that this will help you to solve your homework. I think it's ready to move on to our last problem in the set. So now we have a truly interesting problem here, because we cannot get away with just working our logic through the problem anymore. Of course, we use equilibrium logic, but just seeing the forces is not possible anymore, because we have forces that are not symmetric in these cables, and therefore we have to set up our equilibrium equations. So what we have here is a box or a container with 10 pounds, and that is acting clearly vertically downwards. And then we have AB, AC, and AD with dimensions given. So let's just go ahead and write out our equations. And I start with my conditions. Sum of the forces in X is equal to 0. Sum of the forces in Y is equal to 0. And sum of the forces in Z is equal to 0. And my directions are positive as described here. And now I can get started. 0 is equal to, in the X direction, let's start with our AB. So it's negative AB, right? So minus AB. And what do I need now? I'm pulling in the 2 direction, if I'm not mistaken. Yeah, that's the X direction. So minus 2, of course, I need to calculate the length first. I forgot that. So what is the length here? So the length AB is equal to 2 squared plus 2 squared plus 1 squared. And that is equal to 8 plus 1, so that is equal to 3, right? So that is 3 feet long. And I believe that the other one is no different, because we have 2 and 2 and 1 just in different dimensions, in different directions. So therefore that's also 3 feet. So 3 feet. And so my division is always divided by 3 for cables AB and AC. So now I can continue with my equilibrium equation. I divide it by 3. And for the X direction, I multiply it by 2. And notice the negative. That's important here, right? Now for AC, it's also negative. AC, and again, it's also 3 feet long. But now it's 2, but it's a different 2. So maybe I actually color code this for your understanding. So this 2 would be this 2 here. Whereas this 2 up here is actually this 2. And what else do we have in the X direction? We have AD. So my plus AD. Plus AD. Now in the Y direction, I think I can go ahead and put AB, AC, and there's no AD in it, but I of course have to divide it by 3. And now I am multiplying it in the Y direction by 1. For AB, that's actually positive. So that's this one. And again, let me color code it. So I'm looking at this guy here. And in the AC, it's negative, and AC actually is 2, right? So 2 over 3. And that's a different 2 now, so another color code here. So we're talking about this 2. And there's no other Y component anywhere, so I finished that equation. Now for the Z direction, I have plus AB times 2 divided by 3. And yet another color. So let me color code that as well. That's this one. And for AC, I divide it by 3 and multiply it by 1. And that one is our last number to identify. So I'm going to use gray here. I'm running almost out of colors. But I also need to include AD, which is non-existent. That is true for the one at the top as well. So plus minus nothing. However, I have to include the container, which was given to us with 10 pounds. And that is, of course, in the negative direction, minus 10 pounds. And now I have completely written out my equilibrium equations that now I can solve. That's definitely not my job here to teach you how to solve 3 equations with 3 unknowns. You can choose whichever method you want to. I will say that some students prefer the matrix method. So what would that look like? So minus 2/3 minus 2/3 plus 1. And then we have plus 1/3 minus 2/3 plus 0. And we have plus 2/3 plus 1/3 plus 0. And that would be the matrix, which you have to invert, of course. 0, 0, 10. And keep in mind that we're talking about AB here, AC, and AD. And if you solve this, you can find AB, AC, and AD, but I will not give you the answer right now. This is your job to complete this problem, to see if you are well prepared for these type of problems, because they will end up on your exam, and you definitely need to be able to solve these under time pressure. But I believe this concludes the problem and concludes our understanding of equilibrium in 3D, and we are now well prepared for our homework and upcoming quizzes and tests. So let's move on to our concluding page at the end of this lecture. So now we are ready to conclude the lecture, and you know better than I do what you took away from this class, but please clarify this for you, what is clear and specifically what is muggy for you still. That is a very important aspect so that you can really define what you need to get a better understanding of the material that we covered today. I believe there was many things that we could have taken away from this class today, but only you know what you need to study more. I will tell you now, of course, what I intended to pass along to you with these lectures. So let's clarify that we are able to expand our equilibrium knowledge from 2D to 3D, and all we needed is to add a third direction. So I think we clearly understand that. And that enables us to actually calculate the forces in simple 3D structures. And by simple 3D structures, I mean what we had as a first example. So I can check that off, because if you understand the topics we covered in today's lecture, this was probably the easiest topic. And so we can check that off. You also understand that springs in 3D structures are really no different from springs in 2D structures, and that they are obviously not more complicated. So they definitely don't challenge us when we see springs in 3D systems in the future. And furthermore, we talked about the symmetry in structural systems so that we clearly understand what we can do to reduce or simplify our calculation efforts here. So I believe we can all check that off. And last but not least, we are now able to look at any non-symmetrical structure and calculate the forces from a real-world system, because we can translate the real world into a mathematical model, and we understand that we have 3 equations with 3 unknowns that can help us to solve these cable forces. So I can check that off and I be done with that as well. So now let's take a look at our homework so that we are ready to solve these problems in the real application. So here you see our problems that are upcoming, and surprise, surprise, the first one is an easy one, in quotation marks easy, of course. Easy is everything if you understand how to do it. And of course, our goal is to make these problems easy for you in the future, but also to challenge you, because right now they are not easy because we're learning this stuff, right? So here we have a first approach to solving this, and you can see that you can take advantage of the symmetry of the system. And you have a force given to you in that vertical rope, and there's one rope that pulls up and two ropes that actually spread the force over the x direction. And I think you can solve this fairly quickly if the things that I taught you today in the lecture made sense to you. Then this will be a quick and easy problem. Let's take a look at the next one. Now it becomes interesting, right? So now we actually have a completely random system here. There's no symmetry whatsoever, so you have to set up your equilibrium equations, and you also have to assume that this thing here is made from steel, and steel is just 7.9 times as heavy as water. That's what this here means, right? So you know how heavy a cubic meter of water is. So the steel cube is given with a volume A of something cubic meters. So let's say my A is 5, then I have 5 cubic meters. And I know how heavy 5 cubic meters of water would be, but 7.9 times would be the multiplier for steel. And then I can calculate all the forces here in the cables using kilonewton. And keep in mind that 1 cubic meter of water is equal to 10 kilonewton, right? So you can solve this problem as well. Let's take a look at the next one. Now it becomes really interesting, and this is where the challenge comes in. So here you now have a box with a certain weight given to you, and you have to actually calculate what force it takes here parallel to the y-axis that keeps the system in equilibrium. And note that you have symmetry here, but AB is equal to AC, and that will help you to find the answer. I wish you good luck with that. Again, this is meant to make you think. This is not meant to repeat what we did in the class. So please keep that in mind. Same is true for the last problem, where you have a planter given to you that has a certain weight, and it's supported by this cable structure. And likewise, as before, you have symmetry that can help you to actually solve this problem. So for example, you see that from this anchor point here, or from this 0 point, D is just as far away as C, and is just as high and just as long. So I believe this will help you. And here you have to reverse your logic, because you have to define the anchor point, the height of the anchor point B. That means you have to use geometric logic to hook this hook to the wall. But that concludes our homework overview, and I think you are now ready to tackle these problems. I wish you good luck with that. Please enjoy your engineering mechanics learning experience. This is real fun stuff, at least I tend to think so, because it is so visual and it reflects the real world, and hopefully you get some joy out of solving these problems. Good luck, stay safe, I'll see you next time.